Hello, so this video is for the hybridization project, and the molecule that I chose was iodine trifluoride. Before we begin with the Lewis dot diagram, we first have to figure out if this molecule is octet or non-octet. Looking at the central atom, we know that iodine is a halogen, and this is an indication to show that this is going to be a non-octet molecule. Now that we know this, we can start our Lewis dot diagram with iodine in the middle and placing 3 fluorines evenly spaced out around it. I also put my half in the upper right corner to show that we started with 28 electrons and we minus 6 from the bonds. This is going to leave us with 22 electrons, then we're going to minus 18 from the valence electrons around the fluorines. Now we're left with 4, which we can just put as 2 lone pairs around the central atom, and this is going to be our final Lewis dot diagram. Now looking at the diagram that we just drew, we want to figure out what's affecting our central atom, and in this case we have 5 electron groups, so therefore our geometry will be trigonal-planar. Now using the information that we just figured out, we can start making our 3D diagram. I started by placing iodine in the middle, and with my 2D side, I placed the 3 fluorines. The reason I did this was because when I look at my final 3D diagram, I can see the T-shape better. Then I'm going to put my lone pairs on the 3D side, so the slash is supposed to indicate that it's going into the page and the wedge is supposed to indicate that it's going out of the page. And this is my final 3D diagram. Now when I determine my shape, I know that this is going to be T-shape, like I said before, because the bonds are in the shape of a T, and we can't see the lone pairs. And for my angle, we have 90 degrees, take away 2.5 times 2, because we have 2 lone pairs, which is going to equal 85 degrees. Now we can move on to the next part, which is going to be our condensed electron configuration. To do this, we're looking at our central atom, which is iodine, and the last noble gas was krypton. Then our configuration will follow as 5s2, 4d10, and 5p5. Afterwards, we just make our chart, so on the side we're going to have our potential energy, and at the bottom we're going to have our types of orbitals, so s, p, and d. Then I'm going to draw in my orbitals, and with a red pen I'm going to place in the electrons, with half arrows facing up, followed by pairing it with the half arrow facing down. And this is the condensed electron configuration and condensed energy diagram. Next, I'm going to point an arrow facing down to show my hybridization. This is when we try to identify if we have any special bonds, specifically the ones that affect our central atom. When I look back at my Lewis dot diagram, I can see we have 3 single bonds. This means there's going to be no resonance structure or any pi bonds. If one atom donated their 2 electrons to the other, that would make a coordinate covalent bond. However, in this case, we have sigma bonds because the electrons are shared equally. Also, don't forget to add your 2 lone pairs. So I'll write that on the other side of the arrow, showing that it will affect our hybridization. So when I draw my hybridization, I'm going to draw a chart, and I don't need to label the axes. I'm going to place 5 orbitals based on what we just figured out, and using a red pen to draw in the electrons. By definition, sigma bonds are going to be half arrows facing up, while lone pairs are going to be distinguished by using a half arrow facing up paired by a half arrow facing down. When I'm checking to see if this is correct, I know I'm in my 5th group and I have 7 electrons, which is the same number as the one in my hybridization. With a blue pen, I'm going to figure out the name of my hybridization. On the side, I'm just doing my rough work, so I put s, p, and d orbitals. Then I check off 5 because of my sigma bond and my lone pairs. Then when I'm writing my answer, I put a 4 in the front because this is where my d orbital is, which is my highest orbital. So my answer would be 4sp3d, and we do not need to write the ones. Now we're going to connect back to grade 11 and look at the properties of our molecule. To do this, I'm going to compare my molecule to water. Looking at the diagram, we can tell that water contains hydrogen atoms that are bounded to a highly electronegative oxygen atom, and this is making polar bonds. The attractive force between water molecules create a very strong dipole-dipole force, which means they have a strong intermolecular force. If we look at iodine trifluoride, we can tell that the shape is going to affect our intermolecular forces. The fluorine on the top and the bottom are going to cancel each other out, however the lone pairs cannot cancel out the last fluorine on the left, so this is going to make our overall molecule more negative. If we add an iodine trifluoride molecule, we can tell that this is going to be a negative molecule bonding with another negative molecule, which is creating a weak intermolecular force. A weaker force equals to a lower melting point. So in this case, water is going to have a higher melting point than iodine trifluoride. Based on our understanding, molecules with a very strong attraction are going to be very close together, creating a solid. But iodine trifluoride has a weak attraction and all the molecules would most likely be spread out, so theoretically, this molecule would be in the gas state. If we compare them side by side, when iodine trifluoride is a gas, we can lower the temperature so it can become a liquid like H2O, or even colder if we want it to become a solid. However, since H2O is a liquid, we can either change its state to a gas by increasing the temperature to its boiling point or decreasing its temperature to its freezing point to create a solid. And there it is. Finally, we're done with the hybridization of our iodine trifluoride molecule. I hope you enjoyed this video and thank you for watching.